Alrighty, gang. Welcome back to College Algebra. Today things are, they might seem a little bit awkward on your end. I'm not sure because I'm using my phone's hotspot for internet. Got the cable guy here right now. That's why I'm wearing a mask. And hopefully in the next few minutes, hour, I don't really know. But hopefully in the next short period of time, we'll be able to switch back to my normal connection. I've just been having some issues that they are trying to fix. Today I want to talk about a few things. I want to talk about the upcoming exam, of course. I want to talk a little bit about the roadmap from here to the rest of the semester. We are a little bit crunched for time, just by like one class period. So let's do that. I'm going to turn on my screen share and bring this guy up. So this is MAC1105. Section 007, it's a lecture, and today's date is the 15th? Yeah, 15th, April 2021. Okay. So today, we can talk a little bit more about logarithm and exponential equations, that's fine. I'm going to consider introducing systems, depending on how things go. So that is our last topic, and we do have some extra time here today, and we need to be a little bit efficient with it. And of course, we're going to talk about exams 3 and 4. All right, let's do the bottom line first. So exam 3, that's going to be next Tuesday. So this will be in class next Tuesday. Because I was just today able to publish the project. So there's a project associated with each exam, of course. So exam 3 is going to be next Tuesday, which I think is the 22nd, 21st. No, the 20th. And it's going to cover, everything from exam 2. So log and exponential functions, log properties, and log and exponential equations. It's our last big midterm. There is one more midterm after it, and that's exam 4. Real quick, before I move on to exam 4, I want to say project 3 is up in Canvas now. So I uploaded it this morning. I'll show you here how to get to it. If you go to the announcements for our classes, it's going to be the easiest way to find it. Just above the announcement for today, our lecture, you might have noticed this announcement for project 3. So this is the file right here. So, attach this file for project 3. Same rules as project 1 and 2, download, solve, scan, and upload. Give you a quick look at the thing. So some of it is graphing. I want you to graph the exponential function 2e to the x, state the domain, the range, and any asymptotes. Problem 2 here, I'm asking you to find the inverse to that function. Problem 3, I'm asking for the graph of the base 7 logarithm of x, and then domain, range, asymptotes, find the inverse. Of course, inverses are a part of this test too, right? Operations with functions, one-to-one functions, and their inverses. And then the last few problems here are some word problems that relate to exponential functions. So problem 5 here, you've got 3 different ways to invest some money. You've got $4,500 to invest, and I want to know which one of these will give you the best return. So you're going to invest $4,500 for 4 years, and you have to pick which one of these will give you the best return. You can put it into an account that has interest compounded daily at 3%, into an account that has an effective interest rate of 3.2%. Don't care what the scheme is, we just know the effective rate. And then our last option is to put it into an account with continuous compounding, or compounding with a continuous rate of 3.09%. So one of these is better than the other two. Which one gets us the most money? Problem 6, same sort of thing. It's another word problem. Here only we have a function that models the score a student gets on a test based on how much time they spend studying. We get some information like the student's grade doubles for every 3 hours. We want to find the function g of t, find out how much we get for each additional hour. So what is the growth factor? And then we want to learn how many hours do you need to study to get a perfect score? So what's the solution to g of t equals 100? And then some equations and some expand and combine things. So, you know, stuff that you've been working on. When I said that I was going to prepare a little bit of something for you guys to review for exam 3, this is the something. So please work on this between now and the test. Right? You do still have some material that you can practice with to help get ready for the test. So that's exam 3. Exam 3 is going to be next Tuesday. And I know what you're thinking. That doesn't leave a lot of time for exam 4. And you're right. In this class, though, exam 4 is really not I don't want to say it's not a big deal. It's a midterm exam. It's weighted every bit as heavily as the others. But there's very little material on it. If you look, I guess you guys can't normally see this. Let me show you. So the college, Santa Fe College, for MAC1105 courses, we all use the same Pearson course, right? This is put together by a committee and everybody has to use the same thing because we have a lot of adjuncts teaching this. We don't want people messing with the structure of the course. There's only 2 homeworks associated with exam 4. I'll show you. So the way we're going to do it, on Tuesday of next week, you'll have exam 3. I might introduce a little bit of the systems material today. And then the only 2 homeworks associated with exam 4 are these 2, homeworks 22 and 23. And then there's a quiz here. So that's it. That's the whole shebang. So you've only got these 2 homeworks, systems of equations and systems of inequalities, that are relevant for exam 4. We will cover that material on Thursday. I'll cover some of it today if there's time. The rest of it we'll cover on Thursday. It's a very short bit of material. And then your exam 4, I'm going to give you as a take-home test. So it'll be like a worksheet, basically. I'll publish it on Canvas, you print it, you solve the problems, and then you submit it back on Canvas before the final. So that's how it's going to be structured. So exam 4, the last midterm, this will be given as a take-home on Thursday of next week. And will be due on the day of the final. And just as a reminder, the day of the final for you guys, so do I have your syllabus up here? No, let me grab your syllabus. So the day of the final for you guys is the 27th. So that'll be the Tuesday after. All right, so exam 3 is going to be here. Exam 4 is a take home. I'll give it to you here. You shouldn't have any problem with it. It's generally meant to be kind of a soft thing, right? It's meant to be something that that is relatively easy for you to do. And then on Tuesday of the following week, that's when you have your final, and that is when your exam 4, your take-home exam, will be due. What time is the final? 4:27, 10:30. Final exam. This covers everything. From the whole semester. It's a department final. It's on my math lab. So I loathe the idea of doing tests on MML. I really don't think it's a good way to do things. But because COVID, because we have to have the entire department running remotely, the committee for this course has decided to do the final exam on my math lab. I do have a review for the final for you that we've been working on here. So let me go ahead and pop that. You guys will be able to look at something in MML that is similar in nature to the final. Not the final itself. There it is. All right, so I'll go ahead and open this up now. And we'll have this due on the day of the final. Even the day after, that's fine, I'm fine with that. Okay. All right, so are there any, didn't change the date on that, did I? Are there any questions about the structure of the course or kind of where we're going from here? Any questions about where things are coming from, where they're going, what I need you guys to do to earn your points, have everything go well? So exam 3, this is going to be a tough test, right? This is the test on inverses, exponentials, and logs. It's what we've been sinking all of our time into lately. Exam 4, this is going to be easy. It's a take home, and it's just covering 2 homeworks worth of material. The final exam, of course, this is going to be tough, right? This is the final for college algebra. It's known to be a brutal exam when it's done in person, and it certainly hasn't gotten any easier since moving it onto my math lab. So you really do want to prepare for this. Now, if you're looking for extra study materials, I do have some extra study materials. I've got a paper review for this test. There's the review that's up in MML. I think that's probably your best tool because it will mimic the way the final looks. But if you're looking for extra study materials for the final, don't hesitate to reach out. All right, all that said, today, we can practice a little bit more with log and exponential equations if there's anything like that that you guys would like to see. Otherwise, I am going to introduce systems. So think of today as sort of your review for exam. I think it would be wise to at least solve a few problems. So is there anything from the recent homework or the last few homeworks that you guys would like to take a look at? Any problems that's got you scratching your head or feeling frustrated? It looks like the actual quantitative information didn't copy paste for you there, Mark. So if you could just tell me the homework set and problem number, I would be happy to open it up. Like the numbers themselves didn't make it because I think they're randomly generated. Number 16 from the most recent homework. Okay. So I think we might have done a variation on this the other day, but I'd be happy to take a look because that is one of the tougher problems. It looks like the log and exponential equations only goes up to 14. So is that maybe from, oh no, this is quiz 7. Okay, I'm sorry. Homework 21. Oh. Yeah, okay, so the concentration of bacteria sample is 70,000 bacteria per milliliter. If the concentration triples every 3 days, so that's what's going to tell us how fast our function is growing. That's going to give us the base and kind of power structure of the exponential. How long will it take for the concentration to reach 126,000 bacteria per milliliter? So let's get this down. Is it homework 21, problem number 16? The bacteria concentration right now is 70,000 per milliliter. If this triples, this meaning the concentration, if this triples every 3 days, then how long will it take for the concentration to reach 126,000? Per milliliter. All right. So like all problems of this nature, we need to build a function that models this behavior. And then that's going to tell us, or it's going to allow us to establish an equation whose solution will be the answer to the word problem. The idea of starting with something like c times e to the x is kosher. Well, not quite kosher. It's close to kosher, but it's not the easiest way to go about this. So the number c out front in c times e to the x, that's your like initial value or your initial population, whatever. E to the x has a set growth rate, a set growth factor. So you need to introduce an extra constant. If you wanted to do it like that, you could start with something like c times e to the kx. And then that number k would give you the ability to kind of change the growth rate, growth factor. But there's a much easier way to do this. They've given us this bit of information right here. The concentration triples every 3 days. So remember our doubling time formula? This is a function that doubles the output every k days. And we talked kind of intuitively how we could change this into a tripling time or quadrupling time or halving time, any sort of base multiplication that we wanted to by changing this 2 to something else. So you could start with e to the kx. I want you guys to take a look at this and see if you can come up with a model that would be a little bit easier to work with that's similar to this doubling time function. Yeah, that's excellent. So the function that we're going to use to model this sort of tripling time behavior would be f of x equals c times 3 to the x over k. So this is a function whose output will triple every time x goes up by k. That's the idea here. So for us, we're starting with 70,000. So that's our initial value, our initial population. And we're told that we triple every 3 days. So k would be 3. Therefore, the function f of x that models the concentration of bacteria x days later would be f of x, or sometimes they call it b of t. It would be 70,000 times 3 to the x over 3. So this will be the place to start. This is our model. And then anything we want to do with the problem is going to begin with this. Just one second. So if it goes out again, I should give you a call?
Yeah, how's your law description of cops?
Okay.
Okay.
Yeah, thank you very much. No, I appreciate it.
Yeah, that's when you said 8 to 7.
Sweet. All
All
right.
right.
Thank you for taking
And
the time.
I'll check your plan on that other issues.
Okay, cool. Cool. Thank you. Thank you
All
so
right, no
much.
problem. Have a go.
Take care. All righty. So the question they wanted us to answer, they weren't just asking for this model, right? The question they wanted us to answer was, how long is it going to take for the concentration to reach 126,000 bacteria? So I need to figure out, for what value of x is this thing equal to 126,000? So we need to solve this function, f of x equals 126,000. And now we're just going to start plugging in. So f of x is 70,000. 70,000 times 3 to the x over 3. So that's what's equal to 126,000 here. We can divide over by the 70,000. This is the same sort of equation that we had to solve graphically way back in the previous homework on growth rates, remember? But now we can solve this exactly, because this whole section is about how to solve exponential and logarithm equations. So if I divide both sides by 70,000, I'll get 3 to the x over 3 equals 126,000 divided by 70,000. That's just 126 over 70. You can simplify it more if you want. That's just the obvious thing. Then we can take logarithms. And remember, the way we said to do this is really you should use the natural logarithm. It's the most natural way to proceed. So we're going to take ln of both sides. I'll have ln of 3 to the x over 3 equals the ln of 126 over 70. Now on the left-hand side, this power can come down in front of the logarithm. So this is x over 3 times the ln of 3 equals the ln of 126 over 70. And now that we've got this power down and outside the logarithm, it's just like any other equation. This is now a linear equation, really, because this is just a number. This is just a number. And we need to solve for x. So I'd say maybe first multiply by 3. So x times the natural log of 3 is equal to 3 times the natural log of 126 over 70. And remember, never try to bring numbers inside these things. Don't try to distribute logs. Don't ever try to divide by ln. The only sort of algebra rules that you can use with the logarithm functions are those logarithm properties that we talked about last week. So my last move here is to divide both sides by the natural log of 3. All right, so we're going to bring this whole thing. This is one piece, ln of 3, and the whole piece is going to come over. So this is 3 times the ln of 126 over 70 divided by the ln of 3. Can I cancel the 3's? Can I cancel this with this? No, right? The 3 downstairs is trapped inside of a logarithm. The 3 upstairs is just chilling. These are totally different numbers. The ln of 3, it's like 0.7, 0.8. All right, it's a weird number, but it starts with like 0.8. And this is a 3. 0.8 and 3 aren't the same. We can't cancel those. What about the ln? Can I cancel the ln here with the ln here? Yeah, again, no, right? ln, this is not multiplication. ln is not multiplying 126 over 7 or multiplying 3. It's function composition. It's the natural log of this, natural log of this. It's like f of something, right? It is a function. So those can't cancel. In other words, this is done, right? You really can't do much more with this. So we can feed this to our calculator if we want a decimal. We want to get a feel for how large this number is. I can take 3 times the natural log of 126 divided by 70. Close that parentheses, and then divide that by the natural log of 3. And we get about 1.605. So they wanted to know, this is the number of days, right? F of x measures the concentration of the bacteria x days later. So we started with 70,000 bacteria, triples every 3 days. How many days until we get to 126,000? About 1.5, a little bit over 1.5 days. And this is a good problem. It's about test level. It might be a little bit long for a test question, but any one part of this, like finding that model or solving that equation, would be a perfectly reasonable test question. So are there any questions you have for me about what we did here, why we did it, how we did it? Yeah, you can use the e to the kx model. That is something you can do. It just involves a little bit more work. The number k there that you would have to solve for takes a little bit of time. And certainly, this is kind of like what we were saying about how all logarithm bases, like through the change of base formula, see they're all constant multiples of each other. Exponentials, you could use a base 2 exponential or a base e exponential or a base 3 exponential for any of these problems. But sometimes it's easier if you start with something different. There really isn't a particular word, Matthew, that tells us to use the natural log to solve, or that we'll be using a natural log in the problem. So when we get to this line right here, right, I'm solving an exponential equation. I'm solving an equation where the variable is in the power. That means you're going to use the natural log. You could use a base 3 logarithm here if you wanted. You could use the common log, the base 10 logarithm, if you wanted. But because the natural log is so pervasive, because it's the one that every calculator has a button for, because it's the logarithm that shows up most often in nature, most of the time we do want to use the natural log. But the same, you could replace this natural log with an log, the base 10 log, and the algebra would go exactly the same. So there's really nothing special about the natural log here. It's just the thing that we pretty much always use when we need to solve exponential equations. Other questions or comments on this one? All right, I think Maya wanted to see numbers 9 and 12 from homework 20. So let me go back one homework set here to homework 20. Yeah, these property of logarithms things, these are tricky, right? When I look over exam 3s from MAC1105 classes of yesterday, the logarithm properties questions are the questions that are most often missed or mistakes are made on. So I think it is good that we look at least one or two of these. Number 9 here says to expand this expression as much as possible, rewrite without exponents. And number 12 is asking us to combine these two logarithms into a single log. So let's look at number 9 first. We have the base 9 logarithm of 81 times k to the 7 times x. So you've got a logarithm with a whole bunch of multiplication going on inside. So this is what we have. We want to expand this as much as possible. So this is all about those log properties. Remember what they said. Log properties said that multiplication inside is the same as addition outside. That was our first one. So like log base whatever of x times y is the log that base x plus the log that base of y. This was our first property. Second property was that the base a log of a power, something like x to the y. This is the same as y times the base a log of x. So powers inside can come down in front as multiples. And then the third one said that the base a log of a ratio, something like x over y, can be split up as the base a log of the top minus the base a log of the bottom. So these are our properties. Which one of these properties can I use here? I see inside here a bunch of multiplication. Yeah, 1 and 2. Yeah, very good. So we have to begin with the property 1 stuff, because while this k is being raised to the 7, it's not true that everything inside is being raised to the 7. So once I have like this piece kind of on its own with its own logarithm, then I can use property 2 on him. But first I have to use property 1 to kind of split this up into a log of this, plus a log of this, plus a log of this. So by property 1, the base 9 log of 81 times k to the 7 times x would be equal to the base 9 log of 81 plus the base 9 log of k to the 7 plus the base 9 log of x. So we're kind of using this property twice, once for each of these instances of multiplication. And then with this middle guy, I can go a little further. This 7 can now come down in front of his logarithm. And this is by property 2. right? And that's that property that makes logarithms so useful for solving exponential equations, is that when you take logs, the exponent can come down. Does anybody see anything else we can do here? So I would be pretty happy with this, but I do think there's one more thing we can do if we look really carefully. Yeah, very good, Mark. So the base 9 log of 81, this is just a number. To what power must we raise 9 in order to get 81? We must raise 9 to the 2. Or if you want to be fancy about it, you could write this 81 is 9 squared. And then the base 9 log of 9 squared, that's 2. So this is 2 plus 7 times the base 9 log of k plus the base 9 log of x. And that really is as nice as this could possibly get. As expanded, I should say, as this could possibly get. Questions on this? Right. There will be a problem like this on the test. I'm just telling you, there will be a problem like this on the test where you have to take a log expression and expand it. Yep, this bottom line right here, this is our answer. This is as expanded as that can possibly get. And we also simplified this. If the problem just said expand, I would accept this as a final answer. But if it was expand and simplify, then I would want you to get to this answer down here. Because this base 9 log of 81 can be simplified to 2. But if it just said expand, I would accept this also. Other questions on this one? Alrighty then, there was one other problem here that was requested. I think it was number 12. We want to write this as a single logarithm, as a logarithm of a single expression. So we've got the base 2 log of 9 plus the base 2 log of 3k squared. And they should be putting this stuff in parentheses. This should be the base 2 log of 9 plus the base 2 log of 3k squared. So let's take a look. I want to write as a single logarithm. The expression they give us is base 2 log of 9 plus the base 2 log of 3k squared. All right, when you write logarithms, please do put the inside of the log in parentheses. It makes it clear what's inside the log and what's outside the log. Without that, the notation can get confusing. And I apologize for Anna's poor use of notation. What kind of rules can I use here? Yeah, it's that same property 1 that we used a lot on the last guy, just running in the other way. So this, by property 1, is equal to the base 2 log of 9 times 3k squared. Right? Addition outside the log is the same as multiplication inside the log. And then 9 times 3 is 27. So I would say this is log base 2 of 27 k squared like this. So that gives us our single expression. I think it would be wise to look at one more like this. So first, are there any questions on the step here to here? Years ago, when we taught this class in person, seems like forever ago, I had a considerably more challenging version of this that I would make people do, but I can no longer make you guys do that because we've softened the class quite a bit. But I mentioned the interplay between logarithms and polynomials. This is actually fascinating shit, right? So you can factor if you have a log of a polynomial, you can factor the inside and then use log rules to expand. Rather than doing that here, I'm just going to say, let's write these as a single log. So I'll take one or two of these guys. Let's look at the first one. X times the base 2 log of 3 plus 3 times the base 2 log of x. So same thing, right? As a single logarithm. X log 2, 3 plus 3 log 2x. All right. So let's take a look at this guy. If I wanted to write this expression here as a single logarithm, what would be a good first step? Which property would I use and what would it do? So Kendra and Matthew are both correct. We're going to use properties 2 and 1, and we're going to use them in that order. We have to use property 2 first. So in order to use property 1 to combine, I have to have like just a log of something plus a log of something else with no numbers out front. But I can use property 2 in reverse to bring any number that's out front inside as a power. So that's exactly what we're going to do. First, I use property 2 to bring this x inside as a power and to bring this 3 inside here as a power. Yeah, very good. So what Kendra typed in the chat there is perfect. It's exactly this. It's just hard to type subscripts. So this is by property 2. And then by 1, I can combine these into a single log. This will be log base 2 of 3 to the x times x to the 3. Does everybody feel comfy cozy with this? Mark asks a good question there. So what if I wanted to combine 2 logs with different bases? Could we combine those right away using the rule? The answer is we could not right away. We would have to change one of the log to the other log's base. So in fact, this used to be something I had people do. I think I took it off of this one because it was a little bit too hard. But yeah, it is possible to combine logs of different bases. Like if this was a log base 5 and this is a log base 2, I could use the change of base formula to turn the base 5 log into a base 2 log and then combine them, but not before doing that. So you need to use the change of base formula to make sure the logs all have the same bases. Then and only then could you combine them. So the bases do have to match. You won't see that in this course. I took it out of mine because the department took it out of the final because it was considered a little bit too hard for this level. Okay, would we like to look at more expanding combining logarithms? Is there anything else from the homework that you guys are nervous about, or anything else that you want to look at in preparation for next Tuesday's test? You want to look a little bit more at inverses? Okay. You can do 1 or 2 problems relating to inverses. Let's say identify which function below is 1-to-1 and find its inverse. I'll give us 3 functions. We'll call them f, g, and h. For f of x, I'll use x minus 3 quantity squared minus 1. For g of x, I'll use x plus 1 cubed plus 2. And for h of x, I'll use, how about 2 times the absolute value of x minus 3. Here's 3 different functions. Only one of these is 1-to-1. And there's so many ways to see it that I think, depending on how we want to approach this, I bet some of you, or if you wanted to, you could see which ones of these are 1-to-1. If we're having a hard time recognizing it from any of the algebra, though, there are other tools. We can graph these functions. So first, to figure out which one of these is 1-to-1, I'm going to graph them one at a time and see which ones pass the horizontal line test. I'm going to change my window settings. Yeah, okay, they're normal. So I'm going to graph the function f of x. That's parentheses x minus 3 close parentheses squared down out of the power minus 1. Right, here it is. Is that 1-to-1? Yeah, no, this is not 1-to-1. Why? Why is this not a 1-to-1 function? So I just sketched by hand the graph that I got from my calculator here. Yeah, you could say because it has 2 x-intercepts, but yeah, more specifically, there are lots of horizontal lines. It fails the horizontal line test, right? Fails HLT, the horizontal line test. Remember, if there's any horizontal line that hits your graph more than once, then your function is not 1-to-1. So yeah, you could say because it has 2 x-intercepts, because that is a horizontal line that it hits more than once, but any horizontal line would do the job here. All right, let's look at the graph of G. So I'll come back to my y equals. I'll clear this out because I just want to look at one at a time. That's parentheses x plus 1 to the 3rd power plus 2. Look at graph. Ooh, that's interesting. I can sketch in real quick. So this is the graph of g of x. Is this 1-to-1? Does this pass the horizontal line test? Or does it fail the horizontal line test? Yeah, this one passes the horizontal line test. No matter where I were to draw a horizontal line, it'll hit this graph at most once. This is 1-to-1. So I could skip H in theory, right? Because I say only one of these is 1-to-1. Does anybody know what the graph of this is going to look like? There's not a super nice way to type the absolute value in here. I think maybe if you like scroll around, you might find an abs function. Yeah, there it is. Yeah, it does exist. Good, yeah, it's going to be a V-shaped graph because of the absolute value. So just for fun, remember we did study absolute value graphs at the beginning of the semester. Here's what the graph of h of x is going to look like. So this is also not 1-to-1. Because again, fails the horizontal line test. There's many horizontal lines that hit that guy more than once. All right, so g is our 1-to-1 function. And you see how useful that graphing calculator is, helping us just get a picture. So I want to find g inverse of x, where g of x is equal to x plus 1 quantity cubed plus 2. Do we remember the steps for this? Really, the horizontal line test is the main way, right? There is a way to test for it algebraically, but it's a little bit complicated. There is an algebraic definition of 1-to-1. But we could say, if f of a is equal to f of b, then a has to be equal to b. You can test and see whether this is true algebraically. We looked at one example of that back in the day, but generally speaking, this is quite hard. So pretty much always we're going to want to look at the graph and use the horizontal line test. The other way of thinking about this is no output comes from the same input. So no two different inputs go to the same output, which is saying the same thing as the line above. But sometimes thinking about it this way, like if I gave you a table and I asked you, does that table represent a 1-to-1 function? This would be the nicer way to think about 1-to-1-ness. You could plot the graph from the table too. But yeah, the idea that you can't have two different inputs going to the same output. Or if you have two outputs that are the same, they had to have come from the same input. All right, so we're happy we found that g of x, this guy, is our 1-to-1 function. We want to actually find g inverse now. So how do I do that? So we had a 4-step process here, remember? Our first step was to just write y equals instead of g of x or f of x equals. And then our second step was to solve this for x. So I begin by subtracting 2 from both sides. Then I would take cube roots on both sides. This is a cube root, if you can't see that. And then I would subtract 1 from both sides. So I'd have a cube root of y minus 2 minus 1 equals x. Now step 2 in finding the inverse is to solve for x. This is where in step 3 we would consider any domain issues. If we need to, it's not a big deal for us at this level, but it will be a big deal in pre-calculus if you take that class. And then my last step is just to write down the inverse, because it's this thing. We swap x and y. So I'd have the cube root of x minus 2 minus 1 equals y. And this thing is f or g inverse. So g inverse of x is this thing, the cube root of x minus 2 minus 1. All right, so that's our procedure for finding inverses. When it comes to exponential functions and logarithm functions, this step 2 here, this solving for one or the other, is going to mean solving an exponential or logarithm equation. We can take a look at one such problem because they are in your project, and I do want to give you some more practice with this. But first, are there any questions on what we did here? Okay, so one more of these. So I give you here 2 one-to-one functions, and this time rather than being like linear, polynomial, rational, one of them is an exponential and the other one is a log, and I want to find their inverses. So I'll do f of x first. First we write y for f of x. So this is going to say y equals 4 times 7 to the x minus 1. And then we solve for x. So if I want to solve this expression for x, what's my first step? Yeah, so we've got our y equals here. If I want to solve this for x, what should I do first? Good, yeah, we want to isolate the exponential function, or the exponential portion here, so we got to divide by 4. So I'll have y over 4 equals 7 to the x minus 1. All right, what now? Good, take the natural log on both sides. Of the ln of y over 4 equals the ln of 7 to the x minus 1. And the slick part about that is that this power, x minus 1, is going to come down. So this is the same as saying ln of y over 4 is equal to x minus 1 times the ln of 7, like this. And again, my goal is to solve for x. I'll get this guy alone. So I'm going to divide over the natural log of 7. And we'll have ln of y over 4 divided by the ln of 7 equals x minus 1. And then finally, I can add 1 to both sides. I get ln of y over 4 divided by the ln of 7 plus 1 is equal to x. A little bit complicated. We could use the change of base formula to rewrite this as a base 7 logarithm if we wanted. This is the base 7 logarithm of y over 4. But for now, I'll just go ahead and finish things. So we swap x and y. We think about domain issues here. But there aren't any. So then we swap x and y. So we get y equals the ln of x over 4 divided by the ln of 7 plus 1. And that is your inverse. So I'd say f inverse of x here. I'm out of space on. So f inverse of x here is the ln of x over 4 divided by the ln of 7 plus 1. And I do think it's worth saying that this we could write as a base 7 log if we wanted. That piece right there is AKA f inverse of x is the base 7 log of x over 4 plus 1. I think that just looks nice. And it also is kind of easier to compare the pieces to the original. On the exam or on the final, if showing that the function is one-to-one is a part of the problem, like you're required to do that, then it will say so explicitly. I wouldn't say find the inverse of a function that's not one-to-one. I'll either say, show this is one-to-one and find the inverse, or I'll tell you, you can assume this is a one-to-one function and find its inverse, something like that. All right. Yeah, so I really do like this way of writing the inverse here, but either one would be fine. I think this just looks much nicer. And if you compare it to the original function up here, you can kind of see where the pieces come from, right? The 7 here, the 7 here, the 4 here, the 4 here, -1 here, +1 here. It's a little bit more something that you can wrap your head around. But the important thing is the process, right? The important thing is that you can get from A to B. So however you like to describe the answer. Just make sure you're comfy with this process. Are there any questions here? All right, then I'm going to go ahead and run through this other one. And we want to find the inverse of g of x. And g of x is the base 3 log of x minus 7 plus 2. So my first step here is to write y equals base 3 log of x minus 7 plus 2. What's my next move? Yeah, I'm going to solve for x. So I'll subtract the 2 over. I get y minus 2 equals the base 3 log of x minus 7. Okay. And what is my next step here in solving for x? So we've subtracted the 2 over. Then what? It's not a square root that I need to do here. It's something else. Think back to the lecture from Tuesday. How do I get something out of a log? I'm trying to solve for x here. He's trapped inside this logarithm. Yeah, right. We're going to exponentiate. Remember, to get something out of an exponent, you take logs. To get something out of a log, you exponentiate. So here I'm going to exponentiate base 3. So this will be 3 to the y minus 2 equals 3 to the log base 3 of x minus 7. 3 to the y minus 2 is just 3 to the y minus 2. What is the right-hand side? 3 raised to the power of the base 3 log of x minus 7. What does this simplify to? Yeah, just x minus 7. So remember, if you've got the base a log of a to some shit, that will always just be the shit. And if you have a raised to the base a log of some shit, that will also just simplify to the shit. This is another way of saying that these functions are inverses, right? When you plug one into the other, they eat each other up. So the base 3 exponential and the base 3 log are inverses. So when I plug this into the base 3 exponential, I just get the inside, which is x minus 7. And this is an important concept because it's not just used here, it's used in solving all logarithmic equations. But now we're pretty much done. We just have to add 7. So I have 3 to the y minus 2 plus 7 equals x. And now we can think about domain stuff. There's really no domain stuff to worry about, again, because we're not playing that game where you have to restrict domains. We did talk about that, but it's not something you guys are required to do anymore in this class. But we do need to swap x and y. So it'll give me y equals 3 to the x minus 2 plus 7, which means that is my inverse. So G inverse of x is 3 to the x minus 2 plus 7. And again, kind of compare the pieces here to the pieces of the original. And kind of see where things go and where they are, right? This function was a logarithm function, and it was a base 3 logarithm function. So its inverse should be an exponential function, and it should be a base 3 exponential function, and it is. If you wanted to describe this function verbally, you would say it takes x, subtracts 7 from that, takes the base 3 log of that, and then adds 2. So according to the socks and shoes principle, if you wanted to undo that, you have to do the reverse of each of those things in the reverse order. So the last thing that G does to its input is add 2. So the first thing that G inverse has to do to its input is subtract 2. The thing before that that G did was take the base 3 log. So to undo that, the thing that G inverse does after subtracting 2 is take the base 3 exponential, or exponentiate base 3. And then the very first thing that G did was subtract 7. So the last thing that G inverse should do is add 7. We could have constructed this without using algebra, right? We could have constructed this just using the verbal thing and reasoning our way through it. But this algebra procedure is really important. So make sure you are comfy with it. All right, that is all the time we have today. So we won't be introducing systems today. That's fine. It's, again, a very, very short thing. I will probably, here's what I'll end up doing. Because next Tuesday, we do need to do your exam 3. Exam 4, again, is going to be a take home, but I don't like the idea of just having one day on it. That sucks. So I'll pre-record an extra lecture for you that you can watch after exam 3. And that way you can have a little bit of extra material because the systems content is good. It's meaningful. Pre-calculus will develop the system stuff a lot further. So take a look at that. I'm not really happy with the exam 3 review that exists in MML. There is a prepared one here. I can open it up for you, but I don't think it's really a good sample of the content that we'll be looking at. Let me show you really quick. It wouldn't hurt. I guess I can open it up for you. Plenty of operations with function stuff, but I think it goes a little bit past where we are. Yeah, so this is the thing, is that they, in this, they're assuming that you're only going to do 3 tests in the semester, so that exam 3 would also cover systems instead of having that separately on exam 4. So if I open up exam 3, there's going to be stuff in here that you guys don't know, like the last 5 questions or something. I'll go ahead. Yeah, it's just the last 3 questions. I'll go ahead and open it up. There's no harm in that. But again, you do have a project to work on. So make sure you do the project that I've posted to Canvas and make sure you get the homework done. Those are the best things you can do to prepare for the test. I will go ahead and open this exam test 3 review in MML, even though it's not quite what I would like. That'll be all right. Okay, yeah, we'll pop this up. So, just Today's the 14th, 15th. And we'll have a do more. All right. So that gives you a little bit of extra time to get that review done in case you're not super happy with it. Everything since exam 2, Mark. So let's see, what day was exam 2? Is there not a fucking thing here? Oh, it didn't take it. Okay. All right, so test 2, if you come back into Canvas announcements here. So exam 2 is on March 4th. So everything after March 4th, if you want to, I can come in here to our playlists. So you guys. Everything that comes after March 4th is here. So that was the start of our spring break, right? All right, so here is the link to the playlist starting at the material that is relevant for exam 3. I will paste that into the chat. All right, so if you guys want that, here it is. I'll send it to everybody. That's it. All right, so make sure you get the project completed, make sure you get the homework completed. Those are the most important things, right? The homework, the quizzes, and the project. If you want to, you can go in and do the exam review in MML for test 3. Just be aware that like the last 2 questions are not relevant to us. And yeah, that's it. All right, on Thursday, we can, today's Thursday. So on Tuesday of next week, we will have the test. And then next Thursday, I will teach you about systems. And then we'll have a little take-home test on systems. Between there, I'll give out an extra lecture, but it'll be a pre-recorded thing. That's it, guys. Have a good day.